We have talked about the structure of an atom and how atoms can come together and form bonds to make molecules. And we've looked at the structure and the shape of those covalently bonded molecules. And so now we're going to step even further out and we're going to think about how each of those molecules will interact with another one. And so here we have THC, and we're going to really think in this series of lectures about how does this whole molecule and its shape and its size affect how it interacts with other ones, just like at other THC molecules that are near it in a liquid or a solid or a gas. And so we're going to be thinking about what are the forces that kind of control these interactions between molecules, because it's these forces that are going to dictate a lot of its physical properties. And so the physical properties and physical changes that a molecule can undergo are things that won't actually change its chemical structure or its shape or its size. Those would be chemical changes that would change it. But we can see how it physically changes if it's if it moves between two different physical states, like it's a solid and now it's a liquid, or now it's a gas. And we'll also see things like how viscous it is. So like how slowly it moves if you pour it is a physical property, or its color, its smell, it's also like its surface tension. So like, can a bug walk across it in the liquid state? So all of these things are going to be explained or comparatively explained when we talk about the intermolecular forces that exist between multiple molecules sitting in a sample together. And so let's break this word down a little bit. So intermolecular forces, or sometimes you'll hear intermolecular interactions. But the key part of this first part is inter. And this means between multiple molecules. So like outside of the molecule. And then molecular, that just means we're looking at forces that have to do with the molecules on the molecular level, right? Rather than atomic. And then forces, this is really going to be how the attractions or repulsions that occur between them. And when we bring molecules together, we'll see that these are attractive forces that hold them together or that enable their interactions. We abbreviate this IMF, intermolecular forces. And here's an actual definition of it. It's the forces of attraction that exist between molecules. These affect the temperature of a compound that a compound will vaporize at or freeze at. And also affect if a molecule is fat soluble or water soluble. And so this is really important when we're thinking about cannabinoids and how to extract them out of a plant, or just how they're going to interact with a body. So this series of lectures is going to focus on the physical properties and physical changes that these molecules can undergo, and how the intermolecular forces of just a single molecule will dictate how they interact with one another. Then we'll look at later how those intermolecular forces between our molecules will affect things like which other molecules it's soluble in. So how it interacts with things that are different from it. And this week, it's really looking at how molecules that are all the same interact with one another. All right, so to do this, we're going to need to use a few skills, primarily two, because what we're going to do is compare two molecules and say, all right, well, which one has stronger forces of attraction between it? Because that will mean it probably has a higher boiling point, or we can draw conclusions from that information. So we're going to need to be able to compare size or surface area of molecules, and to also compare their polarity. So I'm going to walk through what it looks like to compare size, and then in the next video, we'll talk about polarity again as a refresher after we learned about it previously when we talked about molecular structure. All right, so when we say size, we do mean the surface area of a molecule. And so when we draw it out, we can kind of imagine that each time we write like an element symbol, it really represents kind of a ball of electron density that makes up its size of that atom. And so when we bring these together, they're going to be overlapping balls of electron density, or spheres of electron density that are going to make up the space that represents the molecule. And so here we have two different ones. They all have carbon and hydrogen bonds, so the atoms themselves are relatively the same size. And one of them has 6 carbons and one of them has only 1 carbon. One has 6 hydrogen, the other has 4. And so if we want to ask ourselves which one of these has the larger surface area, we'll go with the molecule that has the larger number of atoms and takes up more space, just even in our 2-dimensional drawing. So looking at these two, hopefully it's quick to compare and see that the larger size is the C6H6. This is actually benzene. It gets a little bit trickier if your atoms are different, because remember, our atoms have different sizes. So if I'm comparing carbon to something like a radon, the radon molecule, or sorry, atom is much lower down on the periodic table, and it's much larger than carbon, which is higher up. That would be a smaller atom. So we're just going to really look at organic molecules for this. We'll be focusing on carbon and hydrogen and oxygen and nitrogen that are all kind of in about the same region of the periodic table. All right, so now let's compare sizes here. So it was easy to see when there was a lot of carbons versus just a few carbons, the difference in the size. So now we have 2 molecules that both have 6 carbons, and one has 2 more hydrogens than the other, but they're equivalent in about the number of atoms that they have. They're just a little bit different. And so when comparing the size here, I'm again going to ask the question, which one of these two has the largest surface area? And so one of these is in a ring and the other one is stretched out. And so the surface area on the molecule that has just a linear structure is going to have a larger surface area. This is similar to if I compare the surface area I take up when I stretch out versus if I curl up into a little ball. If I curl up into a little ball, I'm going to take up less surface area, or I will have less surface area overall. Because it's the most efficient shape is a sphere for reducing surface area. So we'll need to compare these when we talk about comparing intermolecular forces. And the next thing that we're going to need to be ready to compare is polarity, which we'll talk about in the next video.